So what we're going to do is we're going to take about 30 minutes to enjoy an awesome science show. My name is Thomas, and I'm with the Museum of Discovery, and I'm very excited that we get to join you all today. Now, one of the things I want to do is I want to show you the sponsor of this program. So PPG is a paint company that the Little Rock Group has decided to give us some funding to bring this program to you all today. So we're really happy that PPG has provided this funding so that we can connect with you all virtually. I hope you enjoy the show. It's going to be about 30 minutes long. And then there is a storm outside where we are right now. So if our power cuts out, we will try and reconnect the call as quickly as we can. If it takes more than 5 or 10 minutes, we'll probably reschedule the call. We were able to get through the first one without any issues. So let's hope that that's the case for this one. So with that being said, save your questions for the end. So if you have a question and you want to find out, just write it down. And then at the end, we'll have Mrs. White call on you all to be able to answer those questions. But without further ado, I'm going to turn it over to our educator. So today you're going to get to see the performance from Mr. Sean Carlock.
Good morning and welcome to our awesome science presentation. You guys are about to see all of my favorite demonstrations that we do at the Museum of Discovery right here live just for you. We have some really cool things today, but I must say that this first thing that I'm about to show you is the coolest of them all. I would go so far as to say that I am about to show you the coolest thing that any of you will ever see in your entire life. It's a pretty bold statement, isn't it? Now, what I'm going to show you is dangerous. So in order to protect myself, I have these glasses to protect my eyes. I have these gloves to protect my hands. And how would you feel if I told you that right now, that dangerous substance I'm about to show you is all around you? It's in the air that you breathe. We're going to talk about states of matter today, solids, liquids, and gases. Right now, it's a gas. It's in the air. It's harmless. You breathe it in and out every single day. But if you take a gas and put it under pressure and cold temperatures, you can turn that gas into a liquid. Now, in its liquid form, liquid nitrogen is negative 321 degrees Fahrenheit. And that is by far the coolest or coldest thing you're ever going to see. There's nowhere on Earth that this occurs naturally. It's too warm here. They have to make it in a laboratory. We have to store it in these special containers to help them try to keep it cold. Check this out. Ooh. Now that is just cold, causing the air around it and the moisture around it to change into a fog. As I pour this out, you're going to think it looks a little bit like water. It's clear, it's a liquid. I understand why people think it looks like water. Problem being, water does not do this. Look at all of that fog. Again, that's just from the cold liquid nitrogen causing the moisture in the air to condense. Kind of bubbles and liquid jumps up out of the top of our beaker there a little bit. And I don't think you've probably seen water do that, unless, of course, that water was boiling. That's right. That's what's happening to our liquid nitrogen. Now, for water to boil, it has to be very, very warm. So how can something that I just told you is negative 321 degrees Fahrenheit, extremely cold stuff, how could that possibly be boiling? Well, it's because it's so much colder than the air around it and the beaker that it's inside of. It's causing our liquid nitrogen to boil. So it's boiling, it's evaporating, there's nitrogen gas coming off being released. What we're seeing here again is the moisture in the air getting close to that cold liquid nitrogen, changing into fog. Watch this.
Pay no attention to the man behind the curtain.
See the moisture in my breath, just like on a cold day when you go outside, makes fog. That's what it looks like on a negative 321 degree day. Now, they use this for a lot of really important stuff. In the medical field, they'll use it to cool giant magnets. They use this to burn off warts from people's skin. But here at the Museum of Discovery, we just like to put things in it and see what happens. So what do you say? I've got a few things I want to show you. This is a rubber band. And I'm sure most of you are pretty familiar with this particular apparatus. Is this a solid, a liquid, or a gas? Not a liquid because it holds its shape. If it was a liquid, it would just kind of blue. Is it a solid? Well, it holds its shape, but do most solids do this? Not most of them. You can't grab this table and pull and it's not going to stretch. But this is what we call a polymer, a chain of molecules that are bound together loosely in such a way that they're allowed to move and stretch and line up. Okay, that's what allows this rubber band to stretch out and then go back to its original shape. Now, if we put this inside our liquid nitrogen, it makes it boil even more because this rubber band, from me touching it and from it being in the air around it, it is warm. So it's got heat energy. As we drop it in, it's going to cause that liquid nitrogen to boil and bubble even more. After just a couple of seconds, though, that extra bubbling stops because now that rubber band is really, really cold. And what do you do when you get really cold? You might hold your arms in tight or huddle up close to your friends to try to stay warm. That's what the molecules in that rubber band are doing right now. They're getting close together. They're holding on tight to one another because they're really, really cold. So let's see what happens if we try to use a little bit of force on our rubber band. Here we go. Whoop. It broke. All I did was squeeze it with my hand, and look, it broke into pieces. The rubber band became brittle, meaning that it was very easy for us to break it. It became fragile. But after a couple of seconds, it warms back up again, and we're able to stretch it just like we did before. Now let's watch that one more time. That flew all the way to the door. That was really cool. So it breaks, warms back up again, though, in that warm air. We've taken it out of that cold environment, and it starts to stretch again. Pretty neat, huh? Now I've got another polymer that I want to see how it acts in our liquid nitrogen. But it's different than our rubber bands because this, you can put something inside. It's a balloon. You could put water inside of it, a liquid of some sort, but most often people will put a gas or air inside of this. Have you ever seen where people twist them up and make them into little animals and things? Well, I've brought a couple of my friends along with me I want to introduce you to. This is Siegfried and Roy. They are my trained balloon dogs. They do tricks. So watch. If I put him right here and I say, stay, he'll stay like that for forever. It's really good. What do you mean it's not a good? It's a great trick. Okay, better. Okay. Watch, he does backflips. Whoop. Okay, maybe not. See, what they're really good at is doing tricks in the water, but we didn't have a swimming pool here today that I could use to show you guys the tricks that they do. But we do have this liquid. What do you think would happen if we put our balloons inside our liquid nitrogen? Do you think it's going to pop? Let's find out. Now, we might have to squish a little bit because there's no way that this should fit inside of our beaker. It's a little bit too big, but we'll see if it maybe will squish down. Oh, that fits quite nicely. Maybe we can get two in there. No way that one should fit on its own, let alone two at the same time. But it goes right down inside our beaker. How is that possible? Well, come take a closer look. It looks like our balloons have just kind of shriveled up inside. So let's use a little bit of scientific method here. We're going to observe using our senses. We can see that they've shriveled up. They're not taking up as much space as they did before. That might be because the balloons popped and all of the air came out. But using my hearing, I did not hear the balloons pop. I did not see them pop either. So maybe they didn't pop, but the air was able to sneak out through some kind of a trap door or something that's in the, no, it doesn't make any sense. What if I told you that the air did not come out at all? That the air is still inside our balloons? Remember, our liquid nitrogen exists all around us as a gas until it gets really cold, then it condenses down and becomes a liquid. Well, that's what happens to gases when they get cold. And that gas or that air that was inside of those balloons did the exact same thing. It condensed down under those extremely cold temperatures and became a liquid. That liquid takes up less space than the gas, so the balloon shriveled up. But I can prove to you that the air is still inside. All I have to do is warm it back up. So if we take our balloon out of our super cold environment, that liquid air starts to warm back up. It starts to boil. It starts to evaporate. It changes back into a gas. That gas takes up more space than what the liquid does. It expands out and refills our balloon. Isn't that really cool? Look at that. All right, I'm going to put this down so you can get really close and look at it. Up close and personal. Whoop. Look at that. Now, you probably can't hear this, but it's crackling. It's crackling kind of like if you grabbed a plastic grocery bag and played with it in your hands. That's the sound that that latex, that rubber on that balloon is making as it warms back up and stretches back out again. Look at that. Maybe a little bit of frostbite on his tail, but other than that, no worse for wear. How about a big round of applause for Siegfried and Roy? Woo! Fantastic. Now, let's put it all together and show you something that you've probably seen before. A ball pit ball. Ever been to one of those places where they have the big pit with all of those plastic balls in there? You can get in and climb around. I have discovered through careful observation that these are not good for anything else. They're not heavy enough to play catch. You can't really throw them very far. They don't bounce very well, so you could never use these to play basketball. But what they are good for, putting in liquid nitrogen, of course. Now, a couple of things are going to happen here. Just like our rubber band, the outside edge of that ball is getting very, very cold. The molecules are getting very close together, holding tight to one another. It's starting to become brittle. On the inside of that ball, there is air. That air is getting cold. It's condensing down. It's changing into a liquid. That's creating an empty space in that ball that air used to take up, or a vacuum of sorts inside our little plastic ball. Now, here in a second, I'm going to whack that ball with my tongs, and we're going to break that brittle outer shell of that ball and see what happens because of that vacuum we've now created. Here we go. 3, 2, 1. Look at that. We created an implosion. Now, in an explosion, it goes boo and everything comes out. But since this was a vacuum inside, it kind of collapsed in on itself. All these little pieces went flying off as it shattered. Look at that. It was really cool. Super, super cold. Negative 321 degrees Fahrenheit. Liquid nitrogen. Fascinating stuff. All of this thing is fascinating, but it's also a bit taxing. If you don't mind, I haven't had lunch yet. Could I pause for just a second and have a quick snack? Is that okay? Okay, good. It'll just be a minute. I have to, I brought these for lunch today, but if I just have one, It'll be fine. You guys like Cheetos? I love the poofy ones like this. I also enjoy the crunchy ones. Not sure if I like the spicy hot. Do you guys like the spicy hot Cheetos? Pretty good. Now, I should say, not a good idea to have a snack while you're doing science experiments. If you're not paying attention to what you're doing, you might be talking with your hands. You could accidentally drop something into your experiment. And that would be a waste of a perfectly good Cheeto. Because you saw how cold this liquid nitrogen is. You saw what it did to our balloon animals. They shriveled up inside, they shrunk down, got teeny tiny, itty bitty. Do you think it would be safe for me to put that Cheeto in my mouth? Some of you are nodding yes, some of you are shaking your head no. Well, I guess let's find out. It's very important that I make this very clear to you. I am not putting liquid nitrogen in my mouth. That would be extremely dangerous and ill-advised. So we're going to take this out, and by the time this goes into my mouth, all of that liquid nitrogen has evaporated. All that's left behind is a very cold Cheeto. Woo! Wow, that's cold. And just see all that fog, all that moisture in my breath as it was coming out. That Cheeto's making it super cold, condensing it into a fog that we can see, just like on a cold day when you're outside. Watch this. Woo! Refreshing. But you also notice how it kind of goes all over the place when I exhale. That's going to play a part here in just a moment, as we talk about a little something called a vortex, or a way that air can move. Now, we have a little bit of liquid nitrogen left inside of our beaker here. If I were to leave this, by the time we were ready to use it for our finale, it would be completely evaporated. It would be empty. There would be nothing left inside. So I'm going to pour this back into our dewar, make sure that it stays as cold as it can, and we will use it in a few moments. All righty. Well, look at this. It's snowing. All the moisture in this room is condensing on the outside of that beaker. It's becoming cold, it's freezing, it's turning into ice. We'll pour that back inside there. We'll let that warm back up again. Cold, cold stuff. Negative 321 degrees Fahrenheit. Now, air movement. I'm going to talk to you about a little thing known as a vortex. If I said vortex, kind of sounds like a evil space alien villain or something. Vortex the Destroyer. But could any of you give me the definition of what a vortex is? Maybe. Kind of a tough question. So I'll start with an easier one. How many of you have ever taken a bath? I hope all of you are raising your hands right now. If not, we'll just assume that you're shower people. When you get done taking your bath and you pull the plug, does the water just go straight down the drain? It doesn't, does it? It goes around and around in circles. That is a vortex. Any spinning liquid or gas can form a vortex. And I can show you what that looks like in your bathtub and that water and that liquid using this handheld Vortex Generator. A couple of soda bottles that we stuck together here in the middle. You could make something like this at home. Use tape or something to hold them together. You want to seal that really, really well. Put liquid in one bottle, leave the other bottle empty. Now, if I wanted to get this water into that bottle What should I do? Well, if we think about it scientifically, if we turned this over, gravity would pull that water down from one bottle into the other. Watch what happens. Not much. A little bit of water came through. There were some bubbles. But is this bottle empty? It's completely full. There's no room in this bottle for anything but the air that's already in there. So in order for this liquid to go into that bottle, that air has to go somewhere else. So right now, the air's trying to come up as the liquid's trying to go down. They're running into each other right here, and it's getting stuck like a traffic jam. But if we help it out and give it a little bit of spin or rotation, that will form our vortex and allows our water and our air to switch places. Look at that. Kind of looks like a tornado, doesn't it? Now, in the water, we would call that a whirlpool. And right down the center of it, there's a column of air that acts like a tunnel or a straw, if you will, to allow that air to come right up through the middle while the liquid spins around and goes down the sides. That way, they don't run into each other. They're able to exchange places much more efficiently. Look at that. So that's what it looks like in water, a whirlpool, a vortex. We said it can happen in liquid or in the air, but there's another thing, and it's kind of like a gas, but it's like a super excited gas, and it's called plasma. If you guys are hearing the thunder and the lightning that's going on outside, lightning is plasma. It's electricity flowing through this supercharged gas in the air. Another thing that you've probably seen that we call plasma is fire. So we are going to make a vortex of fire or a fire tornado. In order to do that, we need just a couple of things. We need a vehicle for our fire tornado, and we're going to use this trash can. Now, we put our trash can on a thing called a lazy Susan that allows it to go around and around. That's where we're going to get our rotation. You have to have that spinning air. Now, in order to create fire, you need three things. One, oxygen. Now, the fact that Mr. Thomas and I are here and we're able to still walk around and talk and we've not been rendered unconscious lets us know that there's plenty of oxygen in this room. The second thing that we need is fuel, something to burn. We're going to use a little bit of isopropyl alcohol. Pour that inside of our trash can. Put our container a safe distance away. And last, we need to have a spark or a heat source, something to ignite our fuel. And for that, we'll just use this lighter. Now, if I touch the lighter to that fuel, we have fire. That's pretty easy. If we want to have a fire vortex, that's where the rotation has to come in. Let's give it a shot. Look at that fire tornado. A column of spinning fire. Can you imagine if you went outside one day and you saw that? That would be terrifying, as if a tornado wasn't scary enough if it was made of fire. Whew. Now, luckily, that's not something that we often have to worry about here in the US. Maybe during wildfires, if the wind is just right, it'll whip up a good fire tornado. Now, I've been told, I've never seen it myself because I've never been to Australia, but I've been told that it's possible for this to happen there sometimes. That would be really scary. If anybody knows anyone in Australia, you'll have to send them a message and find out if they've ever seen a real live fire tornado before. Look at that. Spinning gases, spinning liquids. We've seen what it looks like in the liquid. We've seen what it looks like in our plasma. Now let's take a look at what it looks like in the air using my super awesome cups of science. We'll work on that. Now, do you think if I took a big, deep breath, I would be able to blow these cups over? Seems simple enough. Give it a shot. Even up close, I still can't blow them over. Remember when I ate the Cheeto? You could see how that cloud and that moisture came out all different directions. It's really difficult for us to focus our air in small enough a point that it has enough force to push those cups over. That is why I brought this. This is a trash can. Yes, but to the highly trained scientific eye, this is still a trash can. It's what it is. Can't change that fact. But it's no ordinary trash can. It has been modified into a bona fide vortex cannon. We put a rubber sheet on the top of it here, and we put a hole in the bottom of it there. So when you hit that sheet, it causes the air inside to come out through that hole. Okay. Now, thanks to Bernoulli, we know that that moving column of air creates low pressure. Basically saying that the air is going somewhere, so it can't push out against the air around it. So as that air is moving, the higher pressure atmospheric air pushes in to take up that low pressure space. And as it does, it meets that column of air and starts moving with it. The next thing you know, we have rotation. We have spinning gases in the air. That creates our vortex. It allows us to do really cool things like this. The amazing disappearing cup trick. I'm the greatest cup stacker in the world. Water. Now that one's heavy. Oh, there we go. Yes. Pretty cool, huh? I'm like a Vortex Ninja. The problem is we can't see the air. So we can't see what our vortex looks like. When you see a tornado, it's picked up debris and dust and dirt off of the ground and in the air, and that's what you're really seeing flying around. So if we wanted to see what our vortex looked like, we'd have to add something to it. And that's why we have this. This is our fog machine. It's going to create an artificial fog that will allow us to see the air. This is going to act as our dust and our debris. All right. Here we go. What does it look like now? Look at that. Some people say it looks like a circle or a halo or a ring. I prefer donut. Now, the scientific term for that, something that is donut shaped, is a toroid. So we have these little fog toroids that are being made by our vortex cannon. But do they look like a tornado? Well, if you could take a tornado and connect the top of it to the bottom, it would look just like this. The whole outside edge of our little vortex rings is spinning around and around and around. That's what propels that air forward and causes it to move through the air. Look at that. I could do this all day long. But if I did, this whole room would fill up with fog and we'd probably set off the smoke alarm. So I should probably stop and go back because I promised you a liquid nitrogen finale to rival the ages. In order to do this, we've got to have just the right amount of liquid nitrogen. And that's why we have these lines on our beaker. Now that it's had a time to warm up again, all the snow is gone, we'll be able to use that to measure out just the right amount. Put my gloves back on to protect my hands from our super, super cold negative 321 degree Fahrenheit liquid nitrogen. All righty. There we go. Now, over here on the side, I have a kettle that has been heating water throughout this entire show. We're going to take boiling hot 212 degree Fahrenheit water and add it to our negative 312 degree liquid nitrogen. That's a difference of over 500 degrees. If we did that inside of this beaker, it would shatter into a bunch of pieces and I would probably get in trouble. So I'm going to get something that's a little bit stronger to hold our demonstration. We're going to put our liquid nitrogen inside of this metal container, inside of this metal pitcher. Just like that. All right. Now all we need is some really hot water. Now, you can tell that water is hot if you see it boiling or if you can see steam rising off. Now, steam is from that liquid evaporating, changing back into a gas and floating off into the air, just like ours does. But I don't know how well you can see this, probably not super well, but the steam, you notice, is going up. And our cold, cold fog from our liquid nitrogen is going down because warm things go up and cold things go down, right? Heat rises. That's why our steam and our fog are acting differently. Are you ready? This is my favorite part. Here we go. Everyone count down with me. 5, 4, 3, 2, 1. Woo-hoo-hoo! Look at that. Wow. So the second that we throw that hot water into our very, very cold liquid nitrogen, all of that liquid evaporates almost instantly and wants to become a gas again. Remember with our balloon, we talked about how liquid takes up less space than when it's in its gas form. So we had this massive amount of gas that wanted to be released. And because of the shape of our pitcher, it wanted to come straight out the top. And that's why you saw it shoot all the way up. We might have even got a little on the ceiling. Now, all that we have left inside of here is very, very cold air and cold water. You can notice what I was talking about before, how this is coming out and it drops down. That's because it's cold and heat rises and cold things go down. Look at that. Feels really good. Might even, not much. There's a little bit of ice in the bottom, but you probably won't be able to see it. Look at that fog in there, though. That looks really cool. Ooh. Crazy to think that ice could form that fast, but that's how cold this liquid nitrogen is. Extremely, extremely cold. I hope you guys have enjoyed our awesome science presentation. Thank you so much for watching, but don't go anywhere just yet because we're going to take a little bit of time to answer your questions. So if you've got a question, go ahead and raise your hand. Between Thomas and your teacher, we'll figure out who's going to go in what order, and we'll have you unmute your microphone so that you can ask your question, and we will answer it to the best of our abilities. But thank you very much. You're a fantastic audience. Give yourselves a big round of applause.
And let's give Sean a big round of applause. Well done, Sean. That is a really fun show. I hope I got the good camera angles for you guys. I was trying my very best, trying to get it up close. So let's turn it over to Mrs. White. And Mrs. White, if you could call on your students, I will allow people to unmute themselves at this point. So Mrs. White, if you'll call on a student, if the student can unmute themselves and ask their question, we will get through as many as we can. We have a little bit less time because of our delayed start, but let's see if we can get through 3 of our questions this morning. I'm not hearing a question just yet. So if you're still working on getting yourselves unmuted, let me know.
Will you put a ball in? I did. Done. Okay, you're muted. When you put a ball in nitrogen, how does it break?
When we put the ball into nitrogen, how did it break? Was that the question?
Yes. Oh.
It's because it gets really, really cold. So everything's made up of molecules, right? And normally they have a little bit of space, but as they get really, really tight and they hold on to one another, they don't want to move. They don't want to be flexible at all. That rubber band doesn't want to stretch anymore. So when we hit it and use that force to try to move them and they go, no, I don't want to move, that's what causes them then to break. When we hit the ball with the tongs, or when we squeeze that rubber band, it was the molecules refusing to move and standing their ground, you could say, and they just popped.
Excellent first question. Thanks. What is our second question for this program?
Somebody else answer for?
Yeah.
Wants to know about, ask your question, please.
Do we have a second question for this program?
It looks like maybe Robert is unmuted, but I'm not hearing him if he's asking us a question.
All right. Well, if we don't have any more questions, the last thing I want to do is I want to give a big shout out to PPG. Oh, we have one more question.
Where does nitrogen come from?
So as you get to admire the beautiful PPG logo, Sean will explain where nitrogen comes from.
So our liquid nitrogen comes from a laboratory. There's nowhere on Earth where it's cold enough for liquid nitrogen to exist or occur naturally. It would just instantly evaporate and become nitrogen gas. So they have special chambers and machines where they put it in there under cold temperatures and a lot of pressure. And then as they release that pressure, it causes that temperature to drop even further. I'm sure they probably use some vacuum tubes and various different things in that process. It'd be an interesting one to see sometime. I've never actually seen nitrogen go through that process of being liquefied. Yeah, it has to happen in a laboratory, and then we keep it in these special containers to help keep it cold.
All right, folks, that is all the time we have for today. So sorry we couldn't get to every single question, but I hope you guys enjoyed the program. Once again, one more round of applause for Sean Carlock. Excellent show.
Thank you very much.
We hope this program got you excited about science, and hopefully you all will continue to explore in your own way. So thank you again. Have a great day, everybody. Bye.
Bye.